Hi there, this is Jacob Nash Engineering Lessons, and this is Unit 2.1, Lesson 8. And this is on the types of forces, specifically what you can use for free body diagrams. We briefly discussed this in the last unit, but I'm going into more detail in this one. This is part of Standard 2.1.3. There we go. So, there's 6 types that we'll be talking about. These aren't the only ones, but they're the 6 primary ones that you'll need to know to complete Activity 2.1.3. The first one is air resistance. You probably have heard of all of these, but now we're just putting them into words and explaining them more. So, you represent a air resistance force with F air. F subscript air. So, in case you didn't know, when there's a letter and there's something that's above it, it's called a superscript. That's like an exponent, like 2 to the second power. That's a superscript. But when it's down like this, that's called subscript. So F subscript air. That's how you say that. You don't say fair. You just say F subscript air, and it basically means force of air resistance. You don't say A because that can be used for other things. You just have to say air. And this results from falling. So there is naturally air resistance when something falls. So it's kind of associated with gravity somewhat. So here's the free body diagram of a certain cube, and there is a gravity force bringing it down, but it's not completely canceled out, but it slows down this object from falling down because of the air resistance. When people jump from planes, they sometimes, if they're skydiving, they'll go out flat. They're not going to be in the air like they're standing up, like in that motion. They're going to be like they're out like in a star shape horizontally. And also, that's the point of a parachute, because a parachute, it catches the air, and it makes the air resistance force go up, which causes you to fall slower so that you don't get injured once you get to the ground. Same thing applies to a plane's shape. It has wings out so that the plane can't go down as easily. So this is MacGyver, a 80s TV show. This is not the new one that's around these days. It's the classical one. And in the theme song, you can see how air resistance is used for MacGyver. Well, for one thing, he's on a plane, or beside a plane, you can see the wing, but here, just watch this. So, if you saw, that was an episode when Jack Dalton was, I can't really remember. I think the plane was about to crash, and MacGyver accidentally fell out of the plane because he was on the opening thing, and he fell out, but he went in that motion so the air resistance could get caught, but eventually he was able to make his parachute go out, and that was the point, because air resistance goes up. Oh, let's try and do that again. Sorry. Then there's a friction force. This is represented with F of F, force of friction. You have to do lowercase f, because in this case, uppercase F means force, so you have to use a lowercase, or it would just be like force. So you have to just do lowercase for that one. And it results from rubbing. So when you rub your hands together, that makes it actually creates energy, because that's why your hands can heat up like that. But an example includes someone pushing this cube, but it's not going to just go crazy and just all of a sudden like fly and like go crazy and go so fast. Why? Because there's a friction force on whatever surface. Depending on what material there is, like you can't see me obviously, but right now I'm holding my phone. It has a OtterBox on it. If I rub it against my desk and push it, it doesn't move that fast because it has because of the rubber, the friction force is high. But then I have my calculator. It still has rubber things on the bottom of it, but it's plastic mostly, and it can go faster. So snow, you sled in the snow because there's less friction on the snow, but there's more friction on the grass, so it's harder to sled on the grass if you've ever tried to do that. Gravity. This is the obvious force, and this applies to all objects. All these other forces we're talking about, even though it's not shown on here, there is a gravity force. And there's naturally a normal force also, but it's not shown on that. But we'll talk about the normal force also. But gravity is just what brings things down, what Isaac Newton formulated. That apple fell down, and he was like, "Oh, gravity." And this is just a natural force. It occurs with everything. That's basic, and it's F lowercase g. I don't necessarily know why they use lowercase g, because I don't know any uppercase G that's used in this situation, but they just did that. Then normal force, unfortunately there's no picture because this is one that pretty much is invisible. I was talking about this in the last video. It's represented with Fn. It's a natural force, so think about it. Look around you and find something that's sitting on something else. So once again, my phone. It's sitting on my desk. We know that there's a gravity force that's bringing it down because we said that's the case with every force. But if gravity brings it down, why is my phone not just going through the desk and then through the floor and through the ground? Well, because there's a normal force coming up from the desk that makes it stay where it is and causes it to be in equilibrium. So that's just a natural force that's on any surface. So if I put something on top of my phone, like a pencil, the pencil stays on the phone because the phone is having a natural force up. Pull or push. This is represented with FP. So that means this is just resulting from any power source. So you pulling or pushing anything. So a friction force will apply when something is pushed. A gravity force and normal force will also apply so it doesn't fall down. And if it does fall down because there's no surface, then air resistance will come into play also. So I'm pushing my phone on the desk. That's the FP force, F of P. Last one is a tension force. This is represented with F of T, and this occurs with strings or ropes. So this one's not as common in all situations, but it occurs with strings and ropes. So I don't know what this could be, some random cylinder shape on a string. There is a tension force coming down. There's also one coming up because of the connection here, but I didn't put that on there. Sorry about that. An example that you'll see in activity 2.1.3 is a stoplight. How is the stoplight not coming down? Well, there's tension force. Gravity brings it down, but it's staying where it is. And we'll talk more about that in the next video. So this is the end of the video. Please see the next lesson as I go through how to solve the problems about free body diagrams on activity 2.1.3. Thanks for watching.